Imagine holding a small rock in your hand. It seems quiet, still, completely ordinary. But what if I told you that locked deep inside that rock was enough energy to power an entire city for a year? Or, if unleashed all at once, enough destructive force to erase a city from the map, in the blink of an eye? This isn't science fiction, this is the reality of nuclear energy. The story of the nuclear bomb is a story about humanity unlocking one of the deepest secrets of the cosmos. The immense power hidden within the heart of the atom. It's a story that changed our world forever, introducing a weapon so powerful that it reshaped politics, warfare, and our very understanding of survival on planet Earth. This journey began, not with soldiers, but with scientists. Think of Albert Einstein, a man who saw the universe in equations. His famous formula, E equals mc squared, was the key. It's a simple-looking phrase, but it holds a universe of meaning. Mass, the very stuff you are made of, is just a concentrated form of energy. And the amount of energy is immense. The c stands for the speed of light, an incredibly large number. When you square it, the number becomes astronomically huge. A tiny amount of matter can be converted into a staggering amount of energy. Scientists realized they were looking at a recipe for a new kind of fire, a fire stolen from the stars. The discovery of this power came at a dark time. During World War II, nations were locked in a desperate struggle for survival. Scientists on all sides were in a race, racing to see who could turn this cosmic theory into a terrestrial reality. The stakes were higher than in any conflict before. To understand a nuclear bomb, you have to shrink your perspective. I mean, really shrink it down. Forget about cities, buildings, or even people. We have to go smaller, down to the size of a single grain of sand, and then smaller still. We need to journey into the world of the atom. Everything you see around you, the chair you're sitting on, the air you're breathing, the screen you're reading, is made of these tiny things called atoms. For a long time, we thought they were the smallest things possible. The word atom even comes from a Greek word that means uncuttable. But we were wrong. The atom itself is a tiny, bustling universe. At the center of every atom is a core, called the nucleus. It's incredibly small and dense, like a speck of dust in the middle of a giant sports stadium. The rest of the stadium is the space where tiny particles called electrons zoom around. The real magic, the source of all this power we're talking about, is locked inside that tiny nucleus. The nucleus is made of even smaller particles, protons and neutrons, all bound together by an incredibly strong force. Think of it like a tightly coiled spring, packed with potential energy. This force, called the strong nuclear force, is the most powerful force we know of in the entire universe. So how do you get the energy out of this coiled spring? You have to break it. This process is called nuclear fission. The word fission just means splitting. You can't make a nuclear bomb out of just any old element. You can't use iron or carbon or oxygen. You need very special kinds of atoms, ones with large, heavy, and slightly unstable nuclei. Think of them as atoms that are already teetering on the edge, just waiting for a little nudge to fall apart and release their energy. The two most famous ingredients for this cosmic recipe are two elements you may have heard of: uranium, plutonium. These elements are at the very heavy end of the periodic table, meaning their atoms are packed with an unusually large number of protons and neutrons, making them ripe for fission. Uranium is a naturally occurring element. You can find it in rocks and soil all over the world, but it's very rare. It was formed in the cosmic explosions of supernovas billions of years ago, long before our Earth even existed. So, the uranium we find on our planet is literally stardust. However, not all uranium is the same. Most of the uranium you dig out of the ground is a type called uranium-238. It has a very stable nucleus and won't sustain a chain reaction. The special stuff, the kind you need for a bomb, is an isotope called uranium-235. An isotope is just a version of an element with a different number of neutrons. Uranium-235 is the fissile one, the one whose nucleus will split when hit by a neutron. For every 1,000 uranium atoms in nature, about 993 of them are the stable U-238. Only about 7 of them are the precious fissile U-235. This means that natural uranium is not nearly potent enough to create the runaway chain reaction needed for a bomb. It's like trying to start a forest fire with damp wood. You need the really dry, flammable stuff. So, scientists had to find a way to separate the tiny amount of U-235 from the vast quantities of U-238, a process we'll explore soon. It's one of the hardest jobs in all of nuclear science. The other key ingredient is plutonium. Unlike uranium, plutonium is almost non-existent in nature. It's a synthetic element, something we have to create ourselves. Scientists make it inside a nuclear reactor. They take the common uranium-238 and expose it to a shower of neutrons. Some of the U-238 atoms will absorb a neutron. Once scientists identified uranium and plutonium as the key ingredients, they faced a monumental challenge. It wasn't enough to just have the raw materials, they had to prepare them. This process, known as enrichment for uranium production for plutonium, is incredibly difficult and requires massive industrial facilities. For uranium, the task was to separate the rare, fissile U-235 from its far more common cousin, U-238. Both isotopes are chemically identical. You can't use chemistry to separate them. They're like two twins wearing slightly different outfits you can't see from afar. The main difference is weight. U-238 is just slightly heavier than U-235. Scientists had to exploit this tiny mass difference. One main method was gaseous diffusion. First, convert uranium into a gas. Then, pump the gas through barriers with microscopic holes. Lighter U-235 molecules move a tiny bit faster and pass more often. The effect is tiny, so the process must be repeated thousands of times across acres of pipes and filters. The enrichment effort was colossal. The U.S. built a secret city at Oak Ridge, Tennessee. It housed a factory over a mile long. It was the largest building then, and used more electricity than New York City. All to sift atoms one by one for weapons-grade U-235. Weapons-grade means over 90% U-235. Natural uranium starts at about 0.7% U-235, so enrichment was slow and costly. Plutonium followed a different path, but was equally hard. Scientists built the first large-scale reactors to breed plutonium. These reactors weren't for power, they were for producing plutonium. Inside, slugs of natural U-238 were bombarded with neutrons. Over time, some U-238 turned into Pu-239. After irradiation, the slugs were removed, intensely radioactive. Remote-controlled machines dissolved the slugs in strong acids. Complex chemistry separated plutonium from uranium and dangerous waste. That work happened in a secret city at Hanford, Washington, a massive, dangerous industrial feat. By the summer of 1945, the scientists of the Manhattan Project had produced enough enriched uranium, plutonium, to build their weapons. But, a terrifying question remained. Would they actually work? The theories were sound, the calculations were checked and rechecked, but no one had ever detonated a nuclear device before. The uranium bomb design was considered relatively straightforward, a gun-type device where one piece of uranium was fired into another. The scientists were so confident in this design that they never even tested it before using it. But the plutonium bomb was a different story. It was a more complex and delicate machine. The plutonium bomb used a design called implosion. A hollow sphere of plutonium-239, about the size of a softball, was placed at the center of the device. This sphere of plutonium was not dense enough on its own to start a chain reaction. To make it go critical, it had to be squeezed, and squeezed incredibly hard and fast. To do this, the scientists surrounded the plutonium core with a carefully shaped arrangement of conventional high explosives, like TNT. These explosives were designed as lenses that would focus the force of their chemical explosion inward, creating a perfectly symmetrical shockwave. This shockwave would crush the plutonium sphere in a fraction of a microsecond, increasing its density dramatically. This implosion had to be perfect. If the shockwave was even slightly uneven, it would just push the plutonium core aside like a squeezed grape, and the bomb would fizzle. The timing of the dozens of detonators had to be synchronized to within a millionth of a second. This was an immense engineering challenge, and the scientists were not sure it could be done. So, they decided they had to test it. They chose a remote patch of desert in New Mexico, a place they codenamed Trinity. There, on July 16, 1945, they assembled the first nuclear device, nicknamed the Gadget, atop a 100-foot steel tower. Not knowing if their great experiment would result in a dud, a small explosion, or an inferno that would change the world. At 5:29 a.m., the device was detonated. In that instant, a new sun was born on Earth. A flash of light brighter than anything ever seen before illuminated the desert, so bright that it could be seen hundreds of miles away. It was followed by a wave of intense heat, and then a deafening roar that echoed off the distant mountains. A churning, multicolored fireball rose into the sky, forming the now infamous mushroom cloud that climbed miles into the atmosphere. The steel tower was vaporized. The desert sand below it was melted into a glassy green mineral, later named trinitite. The scientists, men who understood the physics better than anyone, were simply stunned into silence. J. Robert Oppenheimer, the scientific director of the project, later recalled that a line from the Hindu scripture, the Bhagavad Gita, came to his mind. "Now I am become death, the destroyer of worlds." The atomic age had begun. The creation of the first nuclear bombs was one of the most secret undertakings in history. The project, codenamed the Manhattan Project, operated under a thick blanket of security. Entire cities, like Oak Ridge in Tennessee and Los Alamos in New Mexico, were built in secret, hidden from public maps and knowledge. The tens of thousands of people who worked there often had no idea what they were working on. A person might spend years calibrating a single dial or monitoring a specific pipe, knowing only that their work was vital to the war effort. This compartmentalization of knowledge was a key safety measure, ensuring that no single person had the full picture of how to build the bomb. Safety was a constant and terrifying concern. The scientists were working with materials and forces that were completely new to humanity. They were handling radioactive elements that could cause sickness and death with invisible, silent rays. There were accidents. Scientists like Harry Daghlian and Louis Slotin tragically lost their lives during criticality experiments, moments when a nuclear chain reaction almost started by accident. They were performing delicate tests, pushing the fissile materials to the very edge of a reaction, and in a split second, a small slip of the hand led to a lethal dose of radiation. These events served as grim reminders of the deadly power they were trying to control. The dangers of these weapons are what make them so uniquely terrifying. A nuclear explosion is not just a bigger version of a conventional bomb. It releases its energy in several destructive forms. First, there is the blast wave, a wall of compressed air moving faster than the speed of sound, capable of flattening buildings for miles around. Then, there is the thermal pulse, an intense wave of heat and light that can instantly start fires and cause severe burns over vast areas. But perhaps the most insidious danger is the radiation. The explosion releases a burst of deadly gamma rays and neutrons, and it contaminates the area with radioactive dust and debris, known as fallout. This fallout can be carried by the wind for hundreds of miles, poisoning the land, the water, and anyone who comes into contact with it. Unlike a conventional weapon, a nuclear bomb keeps on killing long after the initial explosion. The radioactive materials can linger for years, decades, or even centuries, causing cancers and genetic damage for generations to come. This is why nuclear weapons are called weapons of mass destruction. Their effects are indiscriminate, long-lasting, and can render entire regions of our planet uninhabitable. The scientists who built them knew this, and many spent the rest of their lives advocating for control and disarmament, haunted by the destructive power they had unleashed. The story of the nuclear bomb does not end in 1945. In many ways, that was just the beginning. The use of these weapons on the city of Hiroshima and Nagasaki brought World War II to a sudden and horrific end, but it also introduced the world to an era of fear. For the first time in our history, we, as a species, had created the means for our own total annihilation. This knowledge changed everything. It created a new kind of global tension, the Cold War, where superpowers faced each other not on a battlefield, but in a standoff where the first move could easily be the last. The strategy became one of mutually assured destruction, a grim promise that any nuclear attack would be met with overwhelming retaliation, ensuring that there would be no winners, only losers. This reality forced us to think differently about war and peace. The existence of thousands of nuclear weapons, many of them far more powerful than the bombs of 1945, has acted as a dark deterrent. The fear of nuclear winter, we see a global catastrophe where smoke and dust from nuclear explosions would block out the sun and plunge the Earth into a deep freeze, has made large-scale wars between nuclear powers almost unthinkable. We live in a world held in a fragile balance, a peace maintained by the very weapons that threaten to destroy it. It's a paradox that defines our modern age, a constant, low-level hum of anxiety that has been the soundtrack for generations. The science that gave us the bomb also gave us immense gifts. The same process of nuclear fission, when controlled and slowed down inside a reactor, can generate vast amounts of clean electricity, powering our homes and cities without releasing greenhouse gases. Nuclear medicine uses radioactive isotopes to diagnose and treat diseases like cancer, saving countless lives. Our understanding of the atom has opened up new frontiers in science, materials engineering, space exploration. The knowledge itself is not evil. It is a fundamental truth about our universe. The challenge lies in our wisdom, or lack thereof, in how we choose to apply that knowledge. Ultimately, the nuclear bomb is a profound lesson in responsibility. It is a mirror held up to our species, reflecting both our incredible intellect and our capacity for destruction. It teaches us that with great power must come even greater wisdom and restraint. The secrets of the atom cannot be unlearned. The knowledge is out there. Therefore, our survival depends on international cooperation, treaties that limit the spread of these weapons, and a shared global commitment to never again use them. The legacy of the bomb is a permanent, urgent reminder that we are all inhabitants of a small, fragile planet, and we must learn to be careful stewards of the cosmic fire we have stolen from the stars. On this very day, October 8, 2025, we must look at this story not to learn how to build such a thing, but to understand why we must ensure it is never used again. A cautionary tale written in the language of physics, a reminder of the immense responsibility that comes with cosmic knowledge.